What's going on, everybody? So I finally got around to playing around with gain and equalizers and compressors and expanders and limiters. So, finally I have I don't know. I think it sounds okay now. The my full audio field laptop mic, but hopefully this is okay now. Compared to the cancerous ear. I'm not even gonna say that on YouTube, but whatever. So welcome. This is the 5th episode of our differential equation series, and this is the one that I am most excited for, and I've put a lot more time into. This is the stochastic, rough, fractional, and non-local dynamics. I am putting them all together after Lie algebras, after manifolds and tensors, solving differential equations on tensors, and after renormalization. The reason why, stochastic processes and stochastic calculus to solve differential equations is such a kind of just crazy thing to think about. And most people just kind of investigate them a little prematurely before they have solid, measure theory or solid, differential geometry. It's because this is a very rich field. So, again, allow me to stop ranting and let's just kind of get into this. But so, again, we relied on differentiability in the previous episodes, right? But real world phenomena like stock prices or like dust in the wind, right? Or, turbulence in a fluid, they defy that. So they're continuous everywhere, but differentiable nowhere. And one of the core kind of counterexamples to this is just a simple the Weierstrass function as well. I'm kind of ranting now, but anyways, in this episode, we're just going to generalize, right? There's a need for generalization of calculus. We need stochastic calculus because we need to add the idea of randomness and rough paths to handle any wiggliness deterministically. And fractional derivatives are going to bring the idea of non-locality. And this is a complete paradigm shift in the way that we think about mathematics, because smoothness is pretty rare and roughness rules everywhere in the world, right? But just because something is rough doesn't mean that there's not deterministic tools that we can evolve accordingly. So this will build on our previous episodes from the waves of in episode 1, right, where they're not going to get noisy, and the manifolds themselves are from episode 3 are going to host stochastic flows, all right, on flows on the manifolds themselves. So, again, this is more of a conceptual notebook, not so much rigorous. If you want rigorous, go to my initial conditions series and also read books that I have labeled in the Discord that is matching, or that is ascribed to those particular episodes. Okay. So let's look at stochastic calculus and the Ito correction. So at the heart of stochastic calculus is the Brownian motion, which we derived so you should have some idea of what Brownian motion is before we continue. But a fractal basically is the Brownian motion itself is a fractal where paths themselves scale like square root t. And so, and not time itself. So what this looks like is this implies that the square of an increment of the Wiener process is equal to dt. And so this breaks calculus, because originally when you're integrating with respect to something, right, you don't have to account for any variance that's associated with that particular variable, but we do here, okay? And so we're going to see how, Riemann integration will fail again on these wiggles that we're trying to integrate over. So again, for the integral from 0 to t of f of s with respect to integrating with respect to some non-smooth kind of variable, the choice of where we choose to evaluate f matters, right? Normally you would just make like, okay, well, here's a box, right? And then like that box will allow me to create a rectangle to solve an area, right? Well, the Ito integral will say, you know what? Let's just evaluate at the left endpoint, okay? And so just by choosing the value of the function at the left endpoint, we can respect causality, and this would said to be a martingale, or technically a semi-martingale, but it breaks the idea of a chain rule. Chain rule doesn't exist in Ito calculus. All right, doesn't exist. The Stochastic integral, however, will allow us to evaluate at the midpoint of of the Riemann sum, and this will preserve the chain rule but anticipate the future. Okay, so it's not a martingale because it knows the future teleologically. All right, so what does the Ito integral tell us? Well, the Riemann integral, again, I'm sorry, the Ito's lemma, the quadratic variation plays a really key role because the Taylor expansion of the differential of that function, we'll have to add in a plus 1/2 of the second derivative of the function with respect to the process with dx sub t squared. Okay, and as you can see, this Ito, this is a left endpoint, again, kind of process. It's causal and it's martingale preserving, but with quadratic variation for some Ito process here. If we substitute some deterministic drift that we know, and we also have some random variance, and we also use the fact that the variation of the Wagner process itself is just dt, right? Well, then what we'll get is the Ito correction, and this is a volatility-induced drift here. Okay, and the Ito correction is 1/2 of the variance squared with the f double prime. This is essentially the drift that we get that just violates the chain rule. Okay, so okay, now that we get this extra drift term out, we can see where the Stochastic integral and the Ito integral kind of split off. Okay, so obviously they're very different, right? You can see that the Ito integral here is decaying, and let's make the volatility a little bit. Again, if you increase the volatility, it's the same random seed, right? But if you increase the volatility, that gets amplified by how much the Ito needs to be corrected from the Ito correction term, right? And it's decaying. The Ito correction is decaying, and why? Or the Ito process is decaying, and why is that? Well, if you notice, the Stochastic is neutral to the drift. Okay, what does that mean? So for some Ito process, we have a deterministic drift and a deterministic volatility. Again, you can see that it's decaying, but the Stochastic is kind of staying around this middle value. And why is that? It's neutral around an initial value, because the same equation will yield different interpretations. Again, making the Stochastic a little bit more compatible with geometry because it obeys the chain rule, but the Ito decays. And so that just means that we're going to get entirely different interpretations and different physics out of these two processes, right? Whenever we introduce the idea of the randomness and how we choose to integrate, the Ito drift from the noise will tie again to the idea that roughness is creating these extra terms by if we were to just force invariance adjustments. So if we want to be invariant with respect to a martingale, choose Ito. If you want to be invariant with respect to the chain rule in geometry, choose Stochastic. All right. Now, that's what that boils down to. Okay. So for essentially, if we want to connect this to determinism, okay, let's connect noise to determinism. So what we can do is explain that stochastic differential equations, and again, they're called differential equations, yet the derivative is not really defined, right? It's defined in terms of an integral, okay? But stochastic differential equations, let's just go along with this, right? It's kind of a very misleading. There's no derivatives there's no derivatives yet in stochastic differential equations. But we have the Feynman-Kac bridge, and stochastic SCEs aren't really there aren't noisy ODEs. They're actually partial differential equations probabilistically. So what does that mean? For a particle, let's say we have some force that's determining how that particle is drifting, right? We also have some, diffusion coefficient, whatever, square root of that. The ensemble density of all those particles, an ensemble of such particles, we'll call this as a density of those particles, evolves deterministically along or according to and satisfying the Fokker-Planck equation, right? Or this is called the Kolmogorov forward equation, right? And what this shows is that and this is called the Langevin equation, okay? Again, and it describes the Fokker-Planck PDE that is satisfied deterministically. So the Feynman-Kac theorem, or the Feynman-Kac formula, it's a theorem, it's a formula, whatever. We can in reverse solve the backwards PDE, by of course changing our time coordinates, and looking at the boundary, or evaluating the function at subject to some boundary to be equal to some g. Okay, we're just like averaging all of the stochastic differential equation paths. And what this will allow us to do is then say, well, the function itself as a function of x should be the expectation value of that function, or the expected, at the expected value of that final function, evaluated at the boundary with respect to, or with g in the forward coordinate system. Okay. And what that allows us to do is, essentially, tau is the boundary hit time. Okay, that's what that means. So this is a different time coordinate that if we take the expectation value of the function at that time coordinate, given some initial x, that is the solution to the SDE. Okay, this u of x is the solution to this stochastic process. All right, that's what Feynman-Kac formula really tells us. So this is why we can do a Monte Carlo PDE. This means that we can just randomly just throw a bunch of throw a bunch of particles and just see what happens. So let's decrease the number of walkers, and you can see as we move around this x, right, we can shift the amount of particles or the time that they're being or there's a particular time that's being registered when they hit the boundary here. But as you can see, they kind of like do this thing, right? And we have a symmetrical kind of boundary. But these random walker paths are really, precisely just following whatever, or the Wiener process here. And this really shows you that, well, the ensemble of the particles, right? Or the probability density x comma t, right? This is why this is a physics problem. The Feynman-Kac theorem is not a finance problem, and it's usually misrepresented. Nobody explains it correctly. Okay, on the internet, you won't find it. But this is intuitively what's happening, right? The boundary itself from the random motions of these, not colloidal particles, but just randomly drifting particles of being a Wiener process. The solution or the probability density is encoded on the boundary of this entire problem, okay? And it's a reduction of dimensions. It really is, okay? So that's what the Feynman-Kac formula is doing. It's bidirectional, okay? Now, what can we do next? Well, and again, what we can do next is talk about geometry, because geometry itself is going to tell us something about the noise of the process, because we've just been dealing with vanilla, or chill, Levi characterization paths where, we just have a nice Brownian motion, okay? But on manifolds, Brownian uses the Stratonovich the Brownian process itself uses Stradinovich for its invariance. Okay, so for Leibniz to hold, okay, so this chain rule can hold, but Ito needs the Ricci curvature connection. Okay, and this gives us, or Ricci curvature correction, sorry, not connection. We're not super deep into the geometry. Ricci curvature will determine or allow us to correct the curvature. The correction term gives us the Malevin derivative. So Ito process itself is depends on the curvature of the variations in probability space. Okay, so that's also, I'm not going to get super into this, but the curvature of the probability space itself is a way to take the variations of those stochastic processes and do calculus of variations inside of a probability space, and that will allow us to correct the Ito process. All right. So again, what this will lead us to is roughness being this kind of deterministic thing. And in 1998, Lyons, he realized that we can make a deterministic calculus for low Holder regularity paths. Okay, and if anybody has taken measure theory or analysis, the Holder inequality is very important because it describes regularity of a particular process. Okay, so what we can do is invent the idea of a signature. So let's say we have some rough signal. The signal is rough, and we do not know. The signal itself is not enough to know x sub t, but we can know what it's like to iterate integrals over it. All right, and the signature itself is going to be this kind of, series that truncates, or might not truncate. It might be infinite, but we'll have one, and some integral from some s to t with respect to that random variable, and then we'll also tensor the process with itself, okay, to give us the integral over that. Essentially, this will allow us to do the integral over the tensor space, which will then, but itself, again, it's with itself though. But what this signature allows us to do is capture the geometric twisting, and the path itself twists, and the twisting itself is missed by classical stochastic calculus, because we can then get a universal time series feature set from this, right? And so let's look at rough path signatures. So let's look at a basic one where the truncation is trivial. All right, it doesn't matter how we truncate a circle, right? So we can reconstruct this x sub t process, right, for some rough signal. We can reconstruct it with whatever with the signatures, okay, and this will allow us to, and as you can see, it is being reconstructed because it's not like perfectly smooth in comparison to the actual original path that we simulated. This one's a little smoother, this one's a little rougher, but there's a way to extrapolate it. That's all I'm telling you. There's an application to the signature, and so we'll get a universal. Again, these are 2D paths. Again, these are this path itself is two-dimensional, so it's like a circle, and we can look at, again, figure 8 here. So this would be the figure 8, and we can reconstruct it again with this geometric signature. We also get the some spiral that's going towards the middle. This is another path in that space. But if we look at, let's say, kind of a rough scribble, okay, this is a rough kind of path. Well, we can actually kind of mess around with the roughness of the scribble too, right? And I didn't add the random what's it called? So the roughness is just kind of scaling it because the random seed is not changing, but whatever. So assume that, again, this is a rough path, right? Like these are paths that are like super, whatever. But if we can try to reconstruct it, and if we go to higher truncation levels, let's say 6 or whatever, you can see we can approach the path a little bit better and better. And this is given essentially by the signature and where we truncate the signature computation. So again, we also just compress the geometry in an optimal way and detach from probability itself. And roughness, the geometric roughness is the rule, and it allows us to describe Poisson variance without probability, right? Now let's look at fractional calculus and non-local dynamics. So the fractional Laplacian, what we can do is replace Brownian motion with Levi flights, and these are jumps, okay? So if we have negative Laplacian to the s, that's the s order of some Laplacian that we're acting on some function with, okay? And it's a singular integral. This models what we call anomalous diffusion. So this is heavy tails or turbulence, if you will, or in finance, it's Bitcoin, okay? Because that's just kind of the just way of describing this. And the fractional Laplacian has this this precise mathematical definition over for the real numbers and d dimensions or whatever. So that's what it is. That's the form. Just for you to see it. Okay. If we look at fractional time derivatives, a fractional time derivative instead of this is a fractional space derivative for the anomalous diffusion. This is more of a trap model, right? So if you think about it, sometimes particle could get trapped in like a little vortex or something, if you will, right? Or something that's keeping it from actually being purely Brownian or whatever. The time itself at a particular area, it's there's some memory to the path and it remembers where it is and it's history dependent. So this allows us to describe these non-local kind of processes, and we're defining again derivative operators over a particular interval, okay? Because they're non-local, they're not at a point anymore. We're not taking derivatives over points. We're taking derivatives over spaces, okay? That's super important. And this is a more fundamental way of thinking about derivatives as maps, all right? Instead of local maps, we're taking entire intervals. So the Brownian motion, let's look at the Brownian motion first, okay? Because that's kind of rough, no pun intended. And we'll take the number of steps to be a little less, so it's easier on my computer. Okay. So as you can see, we have about 17 numbers of Brownian walkers, right? And we'll get a probability density. It's not perfect. I mean, there's a little bit of randomness. If you believe, Levi characterization of Brownian motion, this should give us eventually, just regular bell curve statistics, right? Essentially, that's what we should have. Okay. After enough numbers of walkers and number of steps, as I go to infinity. All right. Well, these are local paths, right? These paths are just moving and they're evolving to some local rules. Just like if you're looking at a manifold, right? A manifold locally it's pretty flat, right? But globally it's curved. Well, with a random walk locally, it's just moving with some local rules. All right. But if we change to a Levi process, what does this do? Well, as you can see, there's some random jumps, right? And this alpha parameter, again, we're still around the same range-ish, like 250. So there's some jumps over here in that direction. We can change the random seed to look like that. And, we're getting heavy tails in the distribution, right? We're getting heavy tails in our probability density. And that's just a feature of a space that has some Levi stability parameter. And whenever it equals 2, by the way, that gives us Brownian. because it's a perfect diffusion process, right? Where the fractional Laplacian has a stability of alpha to be 2. It's just a perfect double derivative, and it's local. But when we decide to start making it more of an unstable process, then we get fatter and fatter tails until it's just completely like unstable, and we get weird. I mean, look at that. It's just very unstable, and we get weird kind of probability densities and stuff. So the Levi characterization is very closely related to these non-local operators. I'm not going to get super into it in this video, but just know that that's what fractional derivatives are. There's really not much of a mystery to fractional derivatives. They mean something very precise, right? And it just takes a lot of mathematics and background to fully understand what's happening. And you need the Feynman-Kac theorem. You need rough signatures. You need all of these concepts to keep you from becoming an AI psychotic or a math, just to keep you from getting AI psychosis, right? All right, so when you're asking ChatGPT, explain to me a fractional Laplacian or whatever. Okay, so you have to go through everything to really be prepared for the concepts. Okay, so all right, that's enough gatekeeping from you guys. So but yeah, you get spiky log densities and broad spread, whatever. Non-local operators, cool. But okay, now that we have regularity structures, what do we do with that? Okay, enter the KPZ equation for interface growth. I guess a way to think about this would be like if you have some, let's say I'm NVIDIA, or let's say I'm working in Taiwan. I have like a bunch of, I'm trying to make a bunch of thin films for these like semiconductors. I'm making chips, okay? If you know how that works, it's typically done by plasma deposition. So, you'll like bombard some gold, right, with some energy, and the gold is going to randomly, like hit a substrate. It's a stochastic process in and of itself, right? It's going to randomly hit a substrate, and it's going to form, and it's going to diffuse on from some heat, right? There's a lot of stuff going on, but eventually you're trying to deposit a thin film of gold or whatever, so it can be used for like as like a wafer or something for like your phone or your computers, right? And that's what really that's how you should think about stochastic partial differential equations. So we have some stochastic process that is both in space and time. All right. Remember, regular stochastic processes in space depend on a deterministic probability distribution evolution. But with the KPZ equation, this kind of makes it a lot more hard, because this h sub x here, well, h itself is a probability distribution. Okay, h sub x is a distribution. But what does it mean to square a distribution? That doesn't make any sense. You can't square a Dirac delta, right? That's undefined, and the distributions can't multiply with each other. And so so what we have to do, or what Martin Herrer invented in 2014, was the idea of a regularity structure. What is a regularity structure? These are Taylor expansions that are like they have noise symbols, and you need infinite renormalization to define these things. Okay, the KPZ equation. So to do stochastic partial differential equations, you need renormalization. It's infinitely. Okay, and this comes from again from Borel series that we talked about in the very, very first episode of the series. Okay, and right at the end. Okay, and renormalization is this mathematical thing that's been around since like the 1800s. Okay, so it's not a fake field of math. Don't come after me. In fact, it's what defines the idea of regularity structures to begin with. Okay, so let's look at this intuitively. And I'm not. This is not super duper rigorous, right? But what's happening? Let's keep a lot of grid points. And we can look at realizations. This is just the number of processes that are handled. Hold up. Come on. Come on, guys. There we go. There's 6. Okay. What's happening? Again, this is the interface process, right? As a function of space. So it's a space-time random noise. That's what eta is here. This is space-time random white noise. Okay, that's how we're defining it. And you know what this means is we can have kind of a stabilized roughening, right? And the mean height will look kind of something like this. But in order for this process to even exist in the first place, they have to diffuse, right? And the diffusion coefficient will tell you, you know, how regular is this process, and the diffusion will tell you essentially the so let's say I turn my sputtering machine up really high. The argon is flowing in. I'm like, you know, bombarding all of these, like this target material, and it's just like a chaotic mess. I'm putting way too much energy on the diode or the electric field that is defining it. And so, you know, it probably will look something like this, right? Where, you know, allow some time t afterwards, number of grid points. Let's say that there's just no diffusion that's allowed to happen, and nothing's sticking to the substrate. Intuitively, you know, what this is going to look like is, and let's take off the renormalization. So if we don't renormalize, man, it is taking a while to calculate this. I'm so sorry. It's hurting my computer. But that's what I get for trying to do the KPZ equation on a notebook. We'll come back to it, I guess. But essentially, it should blow up, right? Like there should be nothing stable in it. So we need renormalization schemes to, like, you know, make sure that it all works. All right, we'll come back to it. It's taking a while to compute. So the last thing, this is kind of the finale, right? I said the last section was the final boss, but really this is the final boss, because this was coming from a paper in 2015 that actually my mentor in research right now just told me to look at this. He's in the Discord, by the way. So if you guys have any questions about this stuff, go ahead and go to the Discord and let's talk about this if you made it this far. But the KL, or the Karhunen equation, the Karhunen-Loeve equations, Loeve as in the singer. I'm just kidding. I have no idea how to say Loeve. I don't know, man. But this is a Gaussian process, right? And Gaussian processes are these infinite dimensional processes. But what KL said is we can actually expand the process itself. We can actually, it's a theorem, we can state any second order stochastic process as a covariance kernel. And there's some theoretical work that is done on this as well, further at the bottom, but that I've been personally reviewing. But we can just basically have some eigenvalues and eigenfunctions that define any second order stochastic process of the integral operator with a kernel k and some eta that, you know, it's just random. Okay, it's randomly distributed, or it's normally distributed, and they're independent, right? Again, the independently identically distributed becomes a really nice feature, because this expansion is a really optimal one that gets, you know, the second order stochastic process in terms of a deterministic drift, as well as this randomness that is determined by the spectral covariance eigen decomposition. Okay, so if we want to truncate it optimally, or optimal truncation itself will minimize the error of some principal components of those paths, right? So we can explore this in this. This kind of a spoiler. I'm so sorry. And so what this allows us to do for the KL expansion of Gaussian processes, we can look at a Brownian motion, which gives us, for the top right here, we get a truncation, we get like a process that tells us essentially, these paths that are truncated according to the eigenfunction approximation or expansion that we did. And then here we get the top eigenfunctions that we simulate for some truncation level. So let's say we truncate after 1. That's what it looks like. Okay. And then again, this is for an infinite dimensional expansion of any Brownian or any Gaussian process. We also get the reconstruction error. It's just basically, whatever this is minus that for the process. And we also get the eigenvalues spectrum and the explained variance. So we can, this really gives us a lot about how we can optimize and choose when to truncate our particular process. And I would say we could choose right here because there's a region of optimality for when we choose the spectral process that gives us that solution. Okay, and we can look at also for a Brownian bridge. We get a nice, beautiful kind of harmonic eigenfunctions that are integer ratios of each other. And again, you can find that the explained 92% of the variance is explained here. And we can get 93% of the variance. And then we can explain 98% of the variance as we keep going off to infinity, right? And then 99% of the variance is explained for Brownian motion after truncating at like 50 eigenfunctions, right? And as you can see, it's actually pretty fast. Like, this isn't really a slow process, So anyways, last thing we can do is explore fractional Brownian motion, which is dictated by a Hurst parameter, all right? And so what this looks like is if I have 0.5, this is a Brownian motion. I mean, this is fundamentally a Brownian motion. But if we were to increase the Hurst parameter or increase the fractality of our process, as you can see, and let's zoom in really, really close, it's a lot more it becomes a lot less deterministic, or it becomes a lot more less random and more kind of a deterministic path. Whereas if we wanted to make it really unstable, we could also have a Brownian the fractality or the variance that is explained by, that would otherwise be square root of t, right, for that Brownian or for that Gaussian process. If we were to allow it to be a fractional Brownian motion, we can change the degree of the particular roughness of the path, and the roughness is explained by an infinite dimensional eigenfunctions and eigenvalues and bases and all this stuff. So this is really, really cool. So again, we've shattered the idea of smoothness, itself, and stochastics really fixes some of those rules, and the rough path idea generalizes, and fractional derivatives describe the non-locality, or describe a non-local operation that we're doing onto a space that encodes a particular Levi characterization of that space. We get regularity structures to tame infinities earlier from this guy. Oh, and here we go. That's also the other process that I was trying to show you, which was that we need the regularity structures to keep, because obviously, like, if we're sputtering a bunch of gold onto some substrate to make a semiconductor, right? The gold isn't going to clump all the way to infinity or whatever from this, random white noise process and determining this particular, stochastic deposition process. Instead, we have to renormalize it, and to renormalize it, we have to essentially find a way to tame those infinities in a continuous way through time. Okay? And so, and it's not renormalized. Jesus. There we go. So again, the diffusion itself, I have no idea what's happening here. I need to study this a little bit more. But essentially, this is what the KL equation or the KPZ equation should be telling us. All right, so this should allow us to have regularity structures to tame those infinities and those divergences. So everything connects. Roughness is fundamental, and it's actually a deterministic, and invariance is kind of this prevailing idea, again, from the geometric instantiation of roughness itself. Right. So the references here are, Boltzmann for his work on gases, Harrer on structures, Leon on like rough path theory, and there's some more in the notebooks. But thank you guys for watching. Experiment with these interactives once I put them up after I finish everything. And subscribe and stay rough, my friends.